Why, hello. My name is Corbin Harwood, and welcome. Today we're going to start off on a journey through differential equations and linear algebra. And I want to introduce myself a little bit and introduce the course topic to you as well to give you a feel for what you're diving into. Again, my name is Corbin. You can call me Dr. Harwood or Corbin. Either way is fine. I got my doctorate in mathematics, studying specifically numerical methods of partial differential equations. Now, this course touches on a lot of those topics. We'll be focusing on differential equations, which are equations with derivatives, where you have an unknown variable and an unknown rate of change for that variable, and you want to find through this pattern between them what that variable or function is. Now, these differential equations are often used to model and quantify natural phenomena based upon laws of physics, chemistry, biology, economics, ecology, various other uh, subjects that see this application. We'll also see some examples, a lot of examples from engineering, particularly with electrical, and looking a little bit at some structural mechanics. But most of the topics we'll dive into directly relate to mathematics in its wide variety of content. You should be familiar with differential calculus and integral calculus, which are Calc 1 and 2. But this course will also connect with multivariable calculus, or Calc 3, numerical methods, and statistics a little bit, as well as getting into some ideas that uh, push the boundaries towards real analysis or advanced calculus. Okay, so as a mathematician and a scientist, I personally stand in awe of God's handiwork, and I see mathematics as both a gift from God to us, something that we can use, as well as a language of creation. And as a language, there's a lot of grammar that goes into it. There's a mechanics of things of how do you work with words. There's a lot of vocabulary you have to understand and work through. And so we see in this course specifically a lot of that breadth of mathematics fleshed out. Along the way, we will also see and work with some very basic theorems and proofs. Now, this course doesn't require that you have had some practice in proving mathematical concepts before, but it gives you just a slight taste for it. In our upper division math courses, proving is the the level of expectation for all statements that we make. Whenever we're solving problems, we're trying to prove how that solution occurs, or prove how that solution method can be generalized, or prove basic properties of the objects we're analyzing. And so we'll get just a taste for how we can work with theorems and think through and process and outline their proofs as we go through. Along with differential equations, we'll be studying some linear algebra. Now, linear algebra is a branch of mathematics that allows us to handle large collections of information. We often will store them in matrices, or if they're smaller, we call them vectors, columns, or rows, or components. In this course, we'll be studying how we can work with these matrices as if they were numbers to represent how they act on certain structures or vectors. And differential equations essentially is an operation on these matrix spaces, or vector spaces as we call them. Now, just to show how all this connects together, I want to just remind you of a quote from John. 1 John. It says, "Through him all things were made, and without him nothing was made that has been made." This is something that speaks to God's fingerprints on all of mathematics. Some other things that pop up is that the language of creation um, can be seen and used to mathematically describe phenomena. And you may think, well, don't we have words to describe phenomena? Yes. By mathematically, I mean a translation of those words, a translation of those descriptions, whether or not it is Newton's second law, which gives a verbal description of how you can sum up external forces on an object to define its mass times acceleration. Now, that's a verbal description, which can be turned into a mathematical description of ma equals the sum of the forces. And so using that kind of translation, and I just want to bring up another quote by Galileo. The universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in the mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible to comprehend a single word. Galileo believed that we read the heavens, we read the universe around us through mathematics. Those are the vocabulary we use to describe the things we see, to describe the data, to quantify the phenomena that are changing. So that's just want to give you my perspective on how I see mathematics as we dive into it. But I want to just give a word of caution. This is a quote from one of the most famous mathematicians, Leonhard Euler, a Swiss German mathematician. He says that although to penetrate into the intimate mysteries of nature and thence to learn the true causes of phenomena is not allowed to us, we cannot see everything God sees, is what he's saying. Nevertheless, it can happen that a certain fictive hypothesis, his way of describing a differential equation or a model equation, may suffice for explaining many phenomena. What Euler is saying is that we are making assumptions, we're making approximations when we use differential equations and other mathematical models to represent phenomena around us. That is part of the core of mathematics as it's applied to the world around us, is that it doesn't apply perfectly because the world is, in a sense, uh, has error, filled with error, or at least our understanding of it is filled with error. And so when we apply mathematical model to it, we are either um, making an assumption that the world is based upon this pattern precisely when it is not, or but it is closely described by, or the phenomena that we're analyzing is too complex for us to represent. And so we use a simpler model for it. And that model represents the phenomena fairly well to an extent, but not past that. This example is how we see Newton's law of gravity. It is a good model, but it is not quite an exact replica of how the world works, the universe works around us. That's where Einstein's special relativity comes in to kind of fix or add a new level of understanding to what we currently have, make the model more accurate.